Next topic we'll be dealing with is complex stresses and strains. Now I'm telling you this stress should be considered as a tensor. Tensor means it can be scalar or vector used to represent some quantity, and it exists in all directions. Now we already know normal stresses and shear stresses. So if we are considering a material or a part of material as shown in the figure, and I'm going to discuss all the that normal stresses, it can be tensile or compressive, and shear stresses. That is what I have said. 3. How that can be notated and all. So this is basically included in simple stresses only. So here I have considered the dark bordered, that cube shows my material, and all those lines. Now these 3 lines, these 3 larger lines, this and this shows the axis, and this can be x, let this be y, positive, let that denote positive y direction, and let this denote positive z direction. So if I am considering this plane, it is perpendicular to x, and that plane, its normal is x axis, so that can be called as YZ plane. So here we have 1 and 2 that cannot be seen. Opposite to that, 1 and 2 are YZ planes only. So in this plane we have normal stress sigma x where first x denotes the plane. The plane is a plane with its normal as its direction. So second one denotes the direction of sigma, or stress. So sigma x's. So next, if I am showing this one, it is acting along the plane only, no? And this one also, that too is acting along the plane. So both are shear stresses. How can then they be denoted? So shear stresses are given by tau, and this one, it is acting on a plane whose normal is nothing but x, and it is acting in y direction, this stress. So tau xy, and the third one, so it is also shear stress only, tau. It is acting in a plane whose normal is x-axis, so it is nothing but tau x, and it is acting in z direction, so it is tau xz. So I think similarly you can have all those stresses. You can have all those stresses in all the planes named. Now if I am considering the topmost plane, there perpendicular to that plane we have, if I am considering tensile stress sigma, and it is acting in a plane whose normal is y. So sigma y sigma y, and it is acting in a direction y, sigma y. And next, if we are considering this one, it is shear stress only tau. It is acting in a plane whose normal is along y, and it is acting in a direction z. Now this one is also shear stress. Suppose if this is acting in this direction, this should be this way only. Okay. Or the other way. Now this is in clockwise direction, the other two will be in opposite direction. Or this can be the other way too. Then this plane and this plane, the shear stresses should be opposite to that. Anyway, that should be neutralized. So this one tau, and it is acting in a plane whose normal is y, and it is acting in a direction x. So it is tau yx. So I think you got an idea about how stresses can be denoted in all planes, and this is where now we will be moving on to another thing, that is, here we have discussed only in three directions, that is perpendicular and along. Now this same stress can exist in all directions. So we have seen the notations for stresses and strains. Now see a body, if its dimension in one of directions is too small, that is, we may say a thin body, we know stress is nothing but force in that direction divided by cross-sectional area times length of the body divided by elongation in that direction. So if suppose the length is this dimension, which is too small in the considered case, but the lateral dimension, this cross-sectional area, is too large as compared to this length, so in that case, this sigma may approach 0. It can be neglected. In such cases, such kind of conditions wherein stress in one direction can be neglected is called plane stress condition. Plane stress condition. And now suppose we are considering the case of gravity dams or such things. Its length is too large as compared to the cross-sectional area. It is too long. So what we may usually take is consider its width to be 1 and so on. So we have to just consider the cross-sectional area. The length is too large that the deformation it undergo in that direction can be neglected. That is, if delta L by L, if length is this length is too large that this may approach 0. In such cases, strain in one direction can be considered to be 0. So such kind of things as plane strain. Or another example is retaining wall. So we just have to consider the cross section and do all those strains in X direction. If this is X direction and Y direction, and this Z direction can be neglected. That Z direction, strain or analysis in that direction can be neglected since strain can be since strain approaches 0. It is that much long that it can resist the stress in that direction. Now in the first case, that is plane stress condition case, this is sure to undergo strain in that direction. That means if this is X, if this is Y, it is sure to undergo strain in the Z direction. This figure again shows the same only what I have said. Thick body is plane strain. Example is retaining wall. So that is about plane stress and plane strain condition. Next we will move on to complex stress and strain. That is if we are saying about this gravity wall itself, I mean a gravity dam. This is usually how we express gravity dams and all. So here in this direction, it experiences pressure of water. In this downward direction, it experiences self-weight. So a combination of this act on the retaining wall. Now failure may occur along the inclined plane first. Now this landing, the angle at which failure occurs is important. So in complex stresses and strain, we analyze that inclination or the plane of inclination wherein the stresses will be maximum, so that plane may fail first. So that is what middle. Here we have considered so here we have a cube and I have considered an inclined plane as shown in the figure, and this is tensile stress sigma 1, Here again another tensile stress sigma 2 acts. This one. Sigma 2, that is 2. Shear stress. Now, in this inclined plane, we have to find stresses along that plane. So, next we will consider a cubical block of one side, let that be A and B, of sides A and B, and an inclined plane of side C. Let side C be considered. And the inclination of the plane with the vertical is considered as theta. Now we'll move on to stresses. It experiences normal stresses sigma 1 tensile, sigma 2 tensile. Here it is sigma 2 and tau clockwise. So positive direction we are taking everything. So this is the positive direction. So this should be opposing that. Tau. Now this is the inclined plane we are considering. We have to find stresses along this and this direction. For that, what we are doing is putting in or making use of equilibrium of forces. So all these stresses have to be converted to forces first. So sigma 1 converting into force, consider the width to be 1. Consider width of the cubical block to be 1 for easiness. When we are equating all those force equilibrium equations, if there comes a width term, it will cancel out. So for easiness of writing, I have taken that width to be 1. So for sigma 1 will be sigma 1 times A times 1. Now force along this stress is tau times A times 1. Now force along sigma 2 is sigma 2 times B times 1. Along this tau is tau times B times 1. It acts on plane with the side B. So naturally tau times B times 1. So now we can equate the forces along the directions normal and along the plane or inclined plane we have considered. So let those be named as sigma n and sigma t. Since we have already used the term tau, I have just named this as tau t. Now along perpendicular, sigma n, converting that to force, we have sigma n times C times 1. Sigma t times C times 1. So we have all those stresses as well as the forces. Now we can just equate forces along this perpendicular direction and parallel direction to the inclined plane. Now suppose sigma in a perpendicular direction is taken, we have sigma n times c times 1 force can be equated to the components of the main components of the major stresses, major and minor stress. Sigma 1a, its component is this is sigma 1 times a times 1. Now considering this to be theta, in this diagram theta can be expressed, so theta is with the horizontal only. This is theta as well as this is also theta, and sigma n times c force. This is sigma t times c force, and so in this direction we have sigma 1 times a. Then this tau also, that is sigma 1 times a, and here we have 1 tau times b. So it is in the opposite direction. So minus tau times b, and perpendicular direction, or this way if I am considering, we have this tau. So tau times a and sigma 2. Here we have minus sigma 2 times b. So just take the components. Simple. So sigma n times c is equal to sigma 1 a times tau b cos theta. So sigma 1 a minus tau b cos theta, and this one also plus tau a minus sigma 2 b sin theta. Times sin theta. Now this cos theta is nothing but see, this side is a by this hypotenuse length is c. So cos theta can be replaced by a by b, a by c, and sin theta can be replaced as opposite side is b, b by inclined length is c. So it can be sigma 1 A minus tau B times A by C plus tau times A minus sigma 2 B times B by. So somehow now this is sigma n times C times 1 only. Now this C comes out here. Actually then this equation will come out to sigma n is equal to sigma 1 times A by C whole square plus sigma 2 times B by C whole square. When we analyze somehow it should come to be plus tau times 2AB by C. C square. So A by C is sin theta. So this comes out to be sigma 1 sin square theta plus sigma 2 cos square theta plus 2 tau sin 2 theta. That is 2 sin theta cos theta tau sin 2 theta. So this is the equation for normal stress. Similarly, if we are doing that for similar procedure, if we are trying for sigma t, it comes out, we will get a similar equation for sigma t as well. It is so when we are doing sigma t, you can I'll just tell you. When we are doing sigma t, see, we have sigma 1 A minus tau B, its component sin theta, and this one minus tau A minus sigma 2 B times cos theta. So shear stress term will cancel out there, and sigma t, what we are getting, nothing but sigma 1 minus sigma 2 times by 2 times sin 2 theta. So this is how we find or we calculate stresses along an inclined plane and perpendicular to the same. Now, how to find the maximum stresses, how to find the plane where the stresses will be maximum, where the shear stress is maximum, and so on. For that, what we have to do, this sigma n, derive it with respect to theta, and equate it to 0. So there we will be getting stress for a particular value of theta.